Yeah, what is this talk about? So what we're going to do is sort of have a narrative to walk you through what is the problem statement we're trying to address with this technology, and then the solution space. So SPDM is Security Protocol Data Model, and how it touches contributions from various standards groups: Desktop Management Task Force, the UEFI Forum, the Trusted Computing Group. So I'm going to walk you through, what are the constituent elements from those standards bodies, and then hand off to Michael on the POC, and then a specific use case and experience with Surface. So that's kind of how we're rolling through this topic. So what is the problem statement? So we're all very familiar with things like secure boot and measured boot, but that's really applying policy for code running on the host. Hey, I see this operating system loader, this option ROM on a device, and I have this sort of firmware root of trust for verification, and you have the DB. But what about the code you can't see? So device firmware. Within a PCI device, it has its own firmware or some other device. That code execution is actually opaque to the host. So when I plug in one of those, how do I know it can be trusted? And then after boot, how do I know it's a good device? So it's not like this problem statement is new to us. A lot of us use things like an IO MMU to jail a device because, how do we know that it's not, an attack USB fob that someone put an FPGA on versus a veritable device. So, the threat model today is assume these devices can even be hostile, maybe sequester them or jail them with IO MMUs. So what we're going to talk about here is how do we really bring in device firmware as a first-class citizen, just like host executables, option ROMs, and OS loaders, and pre-OS applications. So again, how do I have a platform, I think one presentation I saw a client device where someone said, I have BIOS, that's one firmware, and then I have 16 other firmware devices spread across HID devices, storage devices, etc. So that world of device firmware, namely firmware that's not running on the host, how do I start ascribing some policy around the goodness of that? And that's kind of the problem statement being addressed in this deck here. So the solution, what are we doing about it? So this is where, again, the Security Protocol Data Model, or SPDM, comes in from the Desktop Management Task Force. So this specification has kind of been evolving since 2019, and it's been evolving with other standards groups. And when I describe what SPDM actually is, you'll kind of see why this is the case. Because SPDM is actually a byte stream protocol. It's not a specific set of APIs that run on the host. It's really a set of protocols and transactions between devices. So you see the open compute there. You might do SPDM between maybe a platform root of trust and devices, because maybe your PROT wants to know if a device is good. What we're going to talk about today is the host using it. But SPDM, again, as a byte stream protocol, is very generic. It can be between device to device, not just host to device. So again, SPDM, protocol managed by the Desktop Management Task Force. It's on the 4th generation. And there's actually a project managed by the DMTF called LibSPDM. And that's where my colleague Jiwon Yao is the chair of that actually has a reference implementation of SPDM. Because you'll see when you implement this, you got to have SPDM code running on both sides. And so having a portable C implementation is actually valuable for the interoperability. So I sort of hopefully built up, and wow, this SPDM sounds cool. What is it? So really, again, it's a protocol. It's lighter weight than something like TLS, with a set of commands and responses for different phases of interaction between a requester and a responder. As I said, a requester and a responder could be any class of executable environments. But for this talk, the requester is going to be EFI, again, code running on our host, and the responder will be one of many devices. And so the 4 phases of SPDM, including creating a connection to the device. What version are you? What capabilities? Again, it's kind of like a TLS handshake protocol, but much lighter weight. And then identifying the device, getting digests, and then getting certificates, and then the challenge phase. So say I have a certificate, how do I know it's the veritable device? Generate a nonce, have the device sign it or something else. Again, an authentication protocol. And then finally, measurements. So just like in Secure Boot's awesome. You can validate your PE executables, but for the full scenario, you kind of need measured boot and Secure Boot, because Secure Boot alone doesn't tell you anything about the context, the state. You really want measurements. You want to do higher level protocols like attestation. That same model applies here. It's great that we can verify the device. It said it has this capabilities. It proves it has some certificate, but maybe I want to take the measurement vector and do things like TPM quotes and have an attestation service, so that if there's some issue with this device, some maybe off-machine service can tell me. So again, SPDM provides attestation, authentication. It's a command byte stream between a requester and a responder, and those 4 variants of the SPDM specification define this and add additional capabilities over time to the SPDM protocol itself. So the story we're going to walk you through here is DMTF gave us this cool byte stream protocol. You need requesters and responders. What we've introduced in the UEFI specification is what would it look like with UEFI as a requester. So this is where EFI comes in, and we're at the UEFI Plugfest, and so if I were talking about PROTs doing SPDM, you guys would throw a rocket and say, get out of here, but this is the UEFI venue, and so what is UEFI doing here? So UEFI 210 adds device authentication. So really, if you look at chapter 37, and I think it's in section 37.2, we have sort of augmented the Secure Boot section with device authentication. So again, Secure Boot handles host-based verification, and 2.10 added device authentication. And so wanting to have kind of a familiar design pattern, we have the DB for the host-based. We added a device database to track the trust anchors. We didn't add a dev DBX. That was during the early deliberations. Revocation model is really remove something you revoke versus keeping a revocation list. And then there's also an authenticated variable for enabling, disabling device authentication. And so those are some of the trust anchors. There's a protocol for EDKII device policy protocol that's not in the spec, but will typically abstract some of the things like getting device certificates, challenging the device, and ignoring devices that are in case of a failure. And so you can imagine, like, this would be an augmentation of the PCI bus driver when it sees a PCI device. Instead of assigning bars and trying to run code out of the OROM bar, if it's SPDM capable, now the host can say, hey, underlying device, before I actually interact with you, give you resources, try to run or authenticate your code, are you a, quote, good device? So it adds additional policy on top of, again, that can sort of be a preamble to things like Secure Boot and option ROM verification. And then mentioned measurements and attestation, right? So again, just like Secure Boot is insufficient without measurements, similar here. So the Trusted Computing Group PC client, PC firmware profile has added device measurement. So if you recall, the TCG spec says which PCRs have which components, what are the indices. So that corpus of measurement descriptions have been augmented for device measurements. And so that's where you'll see new measurement objects for device measurements, the certificates, and authentication nonce. You can now have reference integrity manifests that talk about this. So you're essentially leveraging all the goodness that's being built out in the TCG for measured boot, manifests, and extending it into the device space. So again, building on investments that are already there. Code packages, Michaels will talk about that now are just being extended for this device authentication. And it all sounds cool in theory, but how does it look in practice? So I think Michael was going to talk about the POC. I think this was our handoff point, wasn't it, Michael?
Yep.
Okay.
All right. So in EDKII staging, there's a branch called Device Security that has a set of SPDM code added to security package is currently where it's at. There's a library we'll see in the middle, I guess I'll start from there, called SPDM Security Lib. It provides the capability to do basic authentication and measurement. There is it can be linked into any platform to provide SPDM capabilities. There's a module that's inside that branch called SPDM Device Security DIXI that does link the library. That module produces the SPDM protocol, which leverages the libSPDM from DMTF that Vincent mentioned, and it allows you to interact with a target device. It consumes, it's not shown here, an SPDM IO protocol that allows it to know how to interact with the over SPDM with a device. One thing to, I guess, kind of clarify is SPDM operates more at the transport layer. So underneath that, more at the physical bus layer, it may be on something like I2C or SM bus or something like that. It ultimately produces, this module does, using the library EDKII Device Security Protocol. A platform can use, as we see the arrow from the platform going in, the device security protocol in order to get the device policy for an SPDM enabled device and to be notified on the device state. The device database variable stores the root certificate of the SPDM device so that in the future that certificate's available. You can run the SPDM get digest command in order to determine if the variable that you have is valid. From the measurement side, it uses the pretty standard TPM stack with TPM measurement lib from security package, the hash lib. And if you're extending measurements, they'll go to the TPM PCR, and if you're extending a certificate, to the NV index. SPDM can, and I'll talk about this whenever we walk through the surface example, it can provide code measurements, data measurements, also root or certificate chains. And those may go to different PCRs. If it's something like a code blob SPDM measurement, it's going to go to PCR2 likely. Configuration will go to PCR3, and the certificate chain may, because it's security policy related, go to PCR7. So the nice thing about this POC implementation is it does a lot of this work, this kind of like standard routing of information for SPDM. It kind of does that for you and takes care of a lot of the common work that's needed there. So we're going to take a quick look at a use case now. And what I'm going to show here is an example using Microsoft Surface to just kind of show how you may use SPDM in kind of a more end-to-end flow in order to enable IT administrators to like monitor the security posture of managed devices that are remotely attested to using hardware TPM and protected using that TPM data. So we've talked about SPDM being an architecture that allows you, that can help protect a system against components trying to attack the system. It can also be used by a requester like UEFI firmware. Remember, there's this concept of requesters and responders. UEFI firmware would be a requester, the device would be a responder, that's shown in the boxes here. It allows it to identify a device by the device supplying its public certificate. It also allows it to challenge the device to prove that it is who it says it is. This allows you to help high-level use cases handle things like supply chain attacks where devices are swapped out. It also allows enterprises to verify if like hard drives have been swapped within the company and things like that, because the device that was originally provisioned is the one that you're testing against here and checking for. So we'll kind of start with the overall flow. We'll begin by saying that in order for authentication to work properly, a Microsoft certificate chain or some vendor certificate chain that's going to be trusted by the requester is going to have to be provisioned onto the device. This would typically happen in a manufacturing phase. And this is described in the DMTF specifications as like the place where you would do this type of thing. At that point, the device is provisioned. And you see that going to the SSD that's in this box. And I didn't, I guess, call this out, but that box represents the device itself. That's enabled in a service called Device Health Attestation, which is a Microsoft service to attest to the health of a device. The UEFI firmware would act as the requester and use the SPDM protocol in order to do authentication and measurement. The first three, and I didn't show every detailed command that would happen here, the first three commands that happen in any SPDM session are the get version command. This is part of like one of the slides Vincent showed where he had the back and forth transactions happening. The get version command allows you to check for versioning to determine what future command compatibility you have between the requester and responder. The next command that must be sent is get capabilities. This is a way for the requester to determine, in this case the SSD's, capabilities to be able to interact over SPDM. Some of the capabilities that you might need to know is what is your transfer buffer size. I mentioned that different buses were used, so you might need to chunk data between the requester and responder. You can figure that out at that point. You can figure out if the responder is capable of providing certificates. Has it been provisioned with the certificates yet or not? Can it participate in authentication? Can the responder do measurements? It's possible that a responder is a very simple device that does not have the computational power to do something like get certificates and do authentication, but perhaps it can send measurements back. And so that's what get capabilities tells you, is what this device can do. There's also other capability flags there for things like, does it support the get heartbeat command and some of these other commands that are in SPDM. The point is, all that happens, and that's part of setting up the session. The next command that would run is one called, this was also on Vincent's slide, negotiate algorithms. This is where, for asymmetric encryption, you would want to determine what type of algorithms it supports, and then for things like hashing, what type of hash algorithms does it support. This lets you know that you as a requester and the responder are on the same page, and you can work together in order to use SPDM. This is all easier said or easier done in a closed system like a Surface product, because you can control the BOM and you can ensure that devices you're putting in are SPDM capable, that they've gone through the manufacturing process and that kind of thing. So it kind of, in that environment, makes it where you'd expect that things are provisioned properly and working a certain way. You aren't really expecting there to be a lot of these, oh, I sent get capabilities and this just isn't going to work out type of a thing. So the UEFI firmware will get the measurements from the SPDM device ultimately, move those. I showed the library that went through the TPM software stack in order to move those into the TPM PCRs or NV indexes, and they sit there. There is a service, and this is now going into kind of like the Microsoft Azure Attestation kind of flow that's wrapped around this, called the Device Health Attestation Configuration Service Provider, or DHA-CSP. It's a service that runs on the device, and it communicates to a remote service in Microsoft Azure Attestation in order to send that data in number 4 called the DHA boot data. DHA boot data is things like the TCG event log, TPM PCR values, the TPM certificate, the stuff that the service that's in the cloud needs to know in order to validate that this is all, the trusted data from the device. It will then perform its verification and send back an encrypted blob in number 5 to the device. This is for the device to cache locally, and it's going to retain that until a service comes along, like MDM, mobile device management service. And like this case, that would be something like Microsoft Intune, if you're familiar with that. and it would come through in number 6 and send a request and say, hey, I need to know if I can trust you or not. I need a device health verification report. And it will go, oh, I just got that, right, from the DHA configuration service. Let me send it to you. So it's going to send that encrypted blob that it saved, and it's also going to send over a signed blob. The signed blob is the device state at the time that request was made. So this is going to be encrypted blob, is going to be TPM, SPDM stuff, verified by the Microsoft Azure Attestation Service. Signed blob is going to be, this is what my device state is at the time that you asked for it, and I'm sending that to you. So that gets sent in number 7 up to the MDM server. Now it's going to reach out to the DHA configuration service in Azure Attestation, and it's going to send that device health data to it, and then it's now going to process that as its role is in validating these things and send a final device health report back into Microsoft Intune, which is the remote management solution. And that report, which is being sent today, in this, it will now include the SSD health as part of the report. Now, administrators that are using this service can make decisions like, well, was the SSD that was on this system the one that we expected it to be? Were the measurements what we expected them to be? Was the device configuration, measurement what it was supposed to be? And so you can build policy decisions about how to treat this device, whether to allow it to access certain system or network resources, like I showed, like the enterprise managed assets up above, based on the health of that SSD device. So this is just an example. Like I said, it's not necessarily what will happen in a Surface product. I'm just showing like an example of how this could look if you were to use this in a product like that, in order to leverage SPDM to control access to enterprise managed assets. I think finally we have a demo, and I didn't put this into the PowerPoint. So I will switch over now to a what's essentially an animated picture to show you how this works. So I just opened up. The nice thing about SPDM is Jwin has done a lot of the work here. He took both on the specification side and implementation side. And at Microsoft, we have an engineer, Andrew Shefranoff, that has done a lot of the work that I'm helping show. On the Surface side, in terms of working with hard drive vendors in order to enable SPDM and bring it to into the products and allow us to be able to test kind of the UEFI code that Jwin has written and things like that. What I'm going to show here are an SPDM emulator that's available in a GitHub repo called SPDM EMU. It allows you to be able to emulate an SPDM requester and responder so that the two can talk to each other and send messages back and forth. This has been helpful for us in order to test SPDM. So it's if you are interested in it, I recommend you check out the DMTF specs, but also go check out the SPDM emulator work that's there and some of the sample code. And if you're using it for UEFI, definitely look at the device security branch in EDKII staging, because I think it would be really helpful in trying to like understand how you put all this together in order to use it. So now I'm going to drop out of here and see if the file I left is still here on the desktop, which I can't go to, I think. I'll, I guess, cheat by coming over here and do this, and there it is. So this is two just like command prompts open next to each other, and it's showing how the SPDM emulator, the SPDM responder, how they will work together in order to do this. There we go. Now I'll look over here. All right, so this is showing, I don't know if it's going to play or not. I hope by making it a picture, compatibility would be less of an issue. So that that was showing the commands that you can use, but here it's setting up a port on the responder on the right in order to talk to the requester. The requester has sent the initial commands I talked about for like getting the version and the capabilities, and the responder is going to respond back with what it supports. And after this, we're going to, should be going to negotiate algorithms, or that may have happened already. In this case, it's sending get digest. So get digest is checking to see if the cert hashes that the requester has matches the responder. And then it's going to send get certificates to get the certificate chain from the responder and pull it back over, like if the digest don't match. So this is it pulling over those certificates. That's a very long sequence of commands, so I skipped through those. What's this one? This is the challenge. So this is the requester challenging the responder to ensure that it is who it says it is. And then it's going to send get digest again to see if they match this time. Now it's going to send a measurements command. So now it's asking for the measurements that it's going to send over to the TPM. Here it's doing a key exchange command. So this is another command that you can do within SPDM to exchange keys. And that goes on for a while. And there's this is the get certificate signing request command. So during certificate provisioning, you can use get CSR in order to ask a CA to sign the certificate for you. And then there's get certificate after sending get CSR, and then the session ends. So I cut out a lot of stuff. There's like 3 times as many back and forth interactions there than are shown. But this was just meant to show like how you can use those applications in order to do that. And on the very beginning of this image, it will show the command line that you can use in order to see what's done. You can actually specify what commands you want the requester and the responder to send to each other. And what I highlighted at the beginning were the default commands. So all the commands that were sent were part of the default commands that are sent. If you only want to, if you're like trying to interact with an actual device and you only want to send a subset of these commands, you can do that. You can look at what commands you can send, I guess, in the output there. That's, I think, it for us.
Cool. Thank you very much, Michael and Vincent. This was terrific.